6.
So 6?
Okay. I don't know. If you want to go earlier, it's fine.
Yeah, I guess I have to drive home in the dark anyway, so it doesn't
It's
really
probably
make a
better
difference.
to wait, because then there's less traffic. Otherwise, you're just going to be spending a lot of time in traffic.
Yeah, but I think after 8, San Francisco starts to clear up. But
Yeah, that's what I mean. And so then we could, could have early dinner and get underway. So I think if you leave here around 7, you'll get into the Bay Area around 8. So things should be pretty good.
yeah, that's what I would expect.
Yeah.
I think I'm driving against traffic anyways.
Right.
We can start?
Yeah, I think so.
Okay, today we're happy to have Felix Kling, postdoc from Slack. He will talk about the constraint factor theory with machine learning called MadMiner.
MadMiner, yeah.
MadMiner.
Okay, yeah, thank you for inviting me. When I got invited about 1 or 2 months ago, I asked, what is the group interested in, and gave you 2 choices. MadMiner, the tool I will talk about, and Phaser. And I've talked with the guys here about Phaser during lunch, so I guess I presented both already. But now let's talk about MadMiner, a new tool that you can use, for example, to constrain EFTs with machine learning. I learned this morning that today is a special day. It's the International Day of Women and Girls in Science. So let's, for a moment, appreciate all our female colleagues, and let's hope that in the future there will be even more attending talks like this. Okay, so where are we in the field? We have discovered the Higgs already 8 years ago. So the standard model is more or less complete. There are some problems left, but no sign of new physics has been discovered since. So there are a couple of things we could do. We could be happy with what we have achieved and said like, yeah, this is fine, we can describe nature now, and let's retire and do something else. Or, well, we start to look for if there's anything that we are missing, try to explain like the few miracles that are left, and so look for new physics. So what could new physics be? And I'm thinking here about the context of collider physics. Well, maybe physics beyond the standard model will turn out to be something rather obvious. It could be like a dye-something resonance at something GeV, and we find it, and we know immediately what it is. It's easy to look for. Or maybe it turns out to be something more subtle. Maybe there's some slight modification in some, let's say, Higgs couplings that will change some distributions in a subtle way. And this will be the first signs of new physics. Okay, so while this is trivial, let's focus on the second case. There's another thing to appreciate about the time that we live in. We live in an era of data. The LHC is running and collecting more and more data. We have high statistics, so if you look at the Higgs plot from 2012, you see like 5 events that were enough for Higgs discovery in one of the channels. Now we have full distributions. So we can look at those distributions, we can perform multivariate analysis, and we can really extract all the information from it. At the same time, we get interested in more and more complex theories. Like at the very beginning, we measured something like the Higgs coupling strengths. But now what we want to do is measure the Higgs coupling strengths to every individual fermion. Or even better, do something like a Higgs effective field theory, where we would have a Lorentz invariant description of those Higgs couplings. And there can be easily like 20, 30 parameters that are of interest that we, to be consistent, would want to measure at the same time. And of course, those two go along with each other. We need lots of data and lots of distributions to measure a lot of things at the same time. But also to measure those, we need the data. So the developments will go hand in hand. Okay, so how can we test those theories in an era of data? Or differently asked, how can we make sure to extract all the information from data? Okay, so I will first give a small introduction to inference, or what is a problem we try to solve, review what we have done so far, what are traditional inference techniques, then I will present what we are doing, a new approach on solving the problem of how should we measure things. I will introduce a few more statistical concepts, so this will be a rather statistics-heavy talk. The optimal observables and Fisher informations, present quickly our tool, and then walk you through one physics example on how to use it to convince you that this approach really makes things easier for all of us. Okay, so what's a problem? So to really state that, I want to introduce some terminology to make sure that we all know what we're talking about. So on one hand, we have observables. Observables is easy defined, it's everything we can observe. So for example, at the collider, we can observe energies, or transverse momenta, reconstruct the variant masses, or like angular differences. Those are things we can observe. And on the other hand, we want to measure theory parameters. So for all I care about, theory parameters are the parameters in our Lagrangian. We probably rephrase the problem differently, but that's how I would define that. And throughout this talk, I will always write observables, call them X, and have them in blue, and theory parameters are always theta and written in red. And if the projector would be a little bit better, it would probably be easier to see, but yeah, everything that's red will be theory parameter, everything is observables. So the question is, on the one hand, given a theory parameter, how can we predict the observables? And that's an easy problem. And the difficult problem is, given what we observe, how can we infer what the theory parameters are? So what are the theory parameters really describing nature? And that turns out to be a much more difficult problem. The thing that connects the two is the so-called likelihood function. So this is, well, what's the likelihood of observing data given a theory, or what is the likelihood that my data is described by theory? And it's the same function in both cases. I call it p of x and theta. And that's really the key object if you want to make any inference. Closely related is something called the likelihood ratio, which is, as the name says, just the ratio of likelihoods. And it parameterizes how much more likely is some data described by one theory versus another. And why is that useful? Well, there is a statistical lemma, which I will not prove here, that says the log likelihood ratio is the most powerful test statistics to discriminate between two hypotheses. So if we can calculate this log likelihood ratio here, then, well, obtaining like confidence intervals or best values or things like that, it's just a trivial exercise. That tells us what we really want to know is the likelihood ratio. So let's say how much more likely is our data described in one theory versus another. Okay, so the question then is, how can we obtain this likelihood function? Okay, let's see what we usually do. So let's go, so in previous slide I showed two errors, prediction and inference, and we probably all have done prediction before, and there is a very developed tool chain. So at, let's see, LHC, if you're a theorist or experimentalist, you probably have done that before. So let's start with some theory parameters, let's say, well, some Lagrangian, and then we can calculate a matrix element. So we can look at like a pattern level description, which is described by this amplitude here, and we can calculate a matrix element, and this matrix element would be something like a likelihood function of, well, some parameters here that describes the let's say the momenta of all those particles here for a given theory. So at Python level, we could easily calculate how much more likely is it to obtain a certain process with like incoming quarks and outgoing quarks in one series versus another. Okay, then what we do next typically is we have a, well, this is in nature how we observe it, so we do something like shower and hadronization, get a set of, let's say, hadronic particles like pions. And, in principle, given we have an up quark and then calculate, okay, what's the probability that I get like 10 pions out of it? It's something that we can simulate, and there's some underlying description of what's the likelihood function for this to happen. And that's all deep down implemented in some codes like this here. Well, then we have a detector simulation, which then simulates, okay, given I have a bunch of pions hitting a calorimeter cell, what's a calorimeter cell output? And okay, that's also straightforward. There's things like G4 or Delphi simulating that. So again, there's some sort of likelihood function implemented. It might be complicated looking, but in principle known. And then, well, we can take whatever comes out of it and reconstruct observables, maybe run like a jet clustering algorithm. And given that is, in principle, well, complicated, but doable. So we get another sort of likelihood function of observing something given like my output of the detector. And if we would want to know like the full likelihood function of observables given theory, what we would in principle have to do is integrate over all the possible intermediate states, integrate them out, and then we would get this likelihood function here. Those intermediate states or tonal states in the simulator are in statistical terms often called latent variables, and throughout this talk I will call it Z. And well, this we can easily do using our developed chain of Monte Carlo tools, which samples this complicated integral here numerically. Okay, so prediction, simulation, that's an easy problem, already solved. But if we want to do inference, we actually need to know this function here. And we can't really solve this integral in any meaningful way analytically. Like there might be, I don't know, 10 million random variables in G4 when you try to simulate one event, so you can't possibly integrate over all of them. So it's infeasible to actually calculate this integral here analytically or like as a function to get like an analytic expression in any meaningful way. So this likelihood function is intractable. So we have to kind of estimate it. So we need an estimate. Okay. So that's a problem. So how have we solved this problem?
I mean, you can do it for things, something sufficiently simple, right? Like a one-dimensional distribution.
Well, if you have electron goes to muon, you can probably still do that because you can just, if you look at this chain here, okay, there is no pattern shower, no hadronization, detector effects are trivial if you have just muons, and then, yeah, you can do that.
But I mean, a one-dimensional distribution, you could just,
yeah, but,
you could fit to
how many well, interesting physics cases are described by a one-dimensional distribution? So
I'm just saying that's what's kind of been done in practice, right?
That's what I will tell you in, I think, a slide or two. Okay, so let's look again at this likelihood function. Okay, so the full likelihood function, well, so it's given like, well, actually a set of events. So we have like, I don't know, 10 events, and each are described by a set of observables. All that consists of, well, of course, some term that describes how many events should there be. So observed number of events and expected number of events, and performing some Poisson distribution, and then some terms describing how likely each individual event is given a certain theory. And I will show you in a moment how that looks in practice. Okay, so if you take the logarithm of it, it takes the ratios, that all this splits up into terms. There will be one term coming from here, which is just kind of looking at the rate itself, and then some term here which just looks at the kinematics. And this will turn out to be very useful. Okay, so how can we estimate this here, this likelihood ratio? Well, the first and simplest thing, and this is what a lot of people do, is just ignore this term here completely. Just don't look at any distributions and just look at the rate. So this is often called the cut and count analysis. We find some cuts, count the number of events, and then do some Poisson statistics, and then we get a likelihood function. Of course, that means that any additional information in distribution is lost completely. That's easy, but of course not the best we can do. What's the next best thing we can do? Well, we do what Marcus just said. We do some sort of 1D distribution and look at something like a histogram. So we take a hand-picked observable. I call it X prime here. This is typically something that our intuition tells us would be something useful to look at. And this is where we as physicists come in, because we typically have a very good physics intuition and intuitively know which of those is useful or good choice. And then we, well, do a little animation here. So let's say we have two event sets from like blue theory and orange theory, or circle and triangle theory. We fill them into histograms. So you see the orange one here has more events at large values of this observable. Then we can take the ratio bin by bin, and well, then we have our likelihood ratio. Very easy. This is what's also done very often, but of course we ignore the information contained in any other observable, since we only look at one. Well, we can also do it in 2D histogram, but then we would still lose all the remaining observables, and you can't really go more than 2 or 3 dimensional histograms, because, well, then your numbers of bins just were so much that it's just not feasible to do anymore. Okay, what's the next thing you can do? Well, we live in an era of data science, so let's try machine learning. So let's try to train a machine learning classifier to estimate this likelihood ratio. So, example, what people do is, well, and they take the 2 event data sets. It's the same I showed you in the last example. They train a classifier like some complicated neural networks that hopefully, ideally, can separate between this and this theory, get some classifier output which is between, let's say, 0 and 1, and then if it's trained optimally, which is again if, then it's related to a likelihood function in this way. And you can just solve this equation here for what the likelihood function is, and get the likelihood ratio out. And since I've used the same example as on the previous slide, we can compare it to the histogram approach, and you see it agrees with the histogram, although it's maybe not like a very smooth line. This of course works well if the 2 samples I choose here look very different, then it's easy to distinguish. But if they almost look the same, then this approach will have a hard time, because most of the events will be not very useful to distinguish the 2 series. So in practice, it works if you look back at the LHC setting. If you want to have something like signal versus background, this approach works well. If you have something like 2 signals that are rather similar, like let's say in the Higgs effective field theory, where you have like a standard model and some models that's just very slightly different than the standard model, then it will, you will have a hard time training a sufficiently good classifier that can distinguish the 2. Also, if you have a very large dimensional parameter space, then you need to train a classifier for every parameter point, and then if you have 10-dimensional parameter space, and you very easily get like millions of classifiers that you have to train. You don't want to do that. Also, the physics behind it isn't always clear. In some sense, it's a black box. So some people might be hesitant using it in the first place. Well, there is a very physics-motivated solution of solving that, and it's often called the matrix element method. So if we would just be at pattern level, so ignore the shower and detector and anything that has to do with reality, I already told you that we know what the likelihood function is. It's given by the matrix element square. So that's something we can calculate. And so if we would make this approximation that those two are essentially the same, maybe with some hand-picked description of how a detector could possibly change this, then we can just do everything analytically. So this again is some multivariate analysis, so both of them can in principle use all the kinematic information available, but this also offers direct physics insight because we know where it comes from. It comes from a matrix element. It's something we can compute where we can understand the properties. However, this really requires approximation of the detector response, so it has limitations. That's why we haven't used it as much this far. But one thing it's apparent here is that this works really well if you have a problem like looking at two different signals. As long as you can plug the same observables into a matrix element and calculate it, it's really easy, and then you just take ratio of matrix elements to get something like the likelihood ratio. On the other hand, something like signal versus background could be really hard. What is if you have a final state with 4 particles in the final state as a signal and 6 particles in the final state as a background? You can't even take a matrix element ratio anymore because, well, it doesn't have the same input in the matrix element. So both of them have advantages and limitations. Okay. So the natural question that arises is, can we do this matrix element method, which has all the physics inside, but doesn't work at detector level? Could we do that at detector level? That would be really cool, then we don't have all the problems anymore. And that's exactly what we do. So we take the physics inside of matrix element information and the multivariate power of machine learning, put them together, and this will be the approach that I will explain in the next few slides. Okay, so the next section is probably the most important one of the talk. So if there is one section that you want to listen to and then fall asleep afterwards, it's this one here. So everyone wake up again for the next maybe 5 to 10 minutes. Okay. So just to summarize what do simulators do? They, for all practical purposes, are some sort of black box. You put a theory parameter in. It does something inside, samples probably thousands of random variables, like pion momenta and collimator outputs and whatever, and then at the end it gives you auto observables. Okay, but it can give you more. It can also give you matrix elements that it sampled on the way. So this would be a matrix element that depends on the theory parameter and the pattern level momentum. So you can, in principle, calculate for each point you sampled a function that is we call it joint likelihood ratio. So it's just a matrix element, or the ratio of the pattern level matrix elements. This is not what we are after, right? So this depends on the choice of the pattern level momenta, which we simulated on the way. So this is something we actually wanted to integrate out, if you remember. But this is something a generator can give us. Okay. So that's a problem. What we have from the generator is the joint likelihood ratio. So given the simulated events with some pattern level momenta, some observables at the end, and the theory parameter, we get this joint likelihood ratio. But what we really want is just the likelihood ratio that depends on the actual observable data and the theory. So let me introduce a pedagogical example, and now I will move towards having an actual physics example, not just x and theta, but something more physicsy for your intuition. Let's look at a process that's kind of maximally complicated for collider physics, so semi-leptonic TDX production. So the tops are fully leptonic. So the tops decay to leptons and missing energy. So you have plenty of missing energy. Higgs goes to gamma gamma, is a particle in the final state. Typically it's challenging. You include a simple background, and my theory parameter will be a Wilson coefficient in the Higgs effective field series. So we take the standard model Lagrangian and add like one additional operator, this one here. Yeah, if you haven't seen that, the only thing this really does is adds the gluon Higgs coupling at tree level. And the coupling is proportional to this constant CG here. And I define my theory parameter to be 100 times this constant CG, and that the factor of 100 just makes sure that this is an order 1 number for our convenience. And we do the full simulation chain I showed earlier, so matrix element, the shower and hadronization, and detector simulation. And since it's a pedagogical example, and we want to compare it later to what our traditional methods like the histogram give us, and only look at one of the PT of them for compare. So that means that all the other things I could observe or are generated on the way are well, not observable. So latent variables like the neutrino, transverse momentum, or jet charge of flavor that we never observe, or the hadron momenta we typically don't observe, all other observables I haven't mentioned here, everything else. Okay, so how is the likelihood estimated? Let's consider two models. A standard model where the Wilson coefficient is 0, and some BSM model where this parameter is 1, so the Wilson coefficient and the parameterization I had is 100. Okay, and then I sample events according to both theories, and this is shown here. So there is the standard model theory in blue, and there is BSM theory in orange. And well, the obvious difference is there are more orange points at high PT than there are blue points. Okay. Then the next we do is we say, hey, we got from our simulator these joint likelihood ratios. So for each simulated event, we got like what is for the particular choice of path and level momenta in this event generation, what's the ratio of matrix elements, so what is the joint likelihood ratio. And this I now plot on the y-axis. Okay, so why is that useful? Well, you can already see something. You can see that at high PT, this likelihood ratio is high. So that's exactly what we expected. If I have a high PT event, my BSM theory is more likely. Okay, makes intuitive sense. And then, and here comes the magic, we fit a line through. Okay, so this is literally just a sort of best fit, or to make it a little bit more mathematical, we define some loss function, which is saying that's for chi-square fit. So some functional, and then we try to minimize this functional, and the function that minimizes this functional, I claim is the actual likelihood function. Okay. I will not proof that here. There is a proof that would fit on roughly 1 page, so just a little bit of variational analysis. You can find the proof down here.
It's not fit that you fit both set of data, both SM and DSM points?
Yeah, I just fit the points. I mean,
All points.
all points. It doesn't really matter where the points come from at the end, right? Because, well, I just try to fit a line through it. But for a given simulated event, the likelihood ratio is is given, right? It doesn't really matter what I sample it according to. Okay, so how does it work in practice? So we have this loss function here, which is the simplest you could possibly think of. And we try to find the function of this function here that minimizes it. So, okay, how do we parameterize it? Well, as I said earlier, we live in a time of data science and neural networks, so let's use a neural network here to parameterize it, give it like full flexibility of how it could look. And then we use, well, all the Python libraries for stochastic gradient descent to find the minimum, and that's it. Okay. So essentially what we have done is we have reduced the problem of estimating the likelihood function So essentially it's a problem of, almost the entire problem of inference to fitting a function. And fitting a function is, I mean, that's not such a big problem. So this is, yeah. So all they kind of know how to do this.
I think, I'm sorry, I think
Yeah.
there's something I'm really, I thought, so, no, I think I'm just, I don't know, this is not, I realize this is not a question, but I'm lost, so.
Okay, no, that's good. Thanks for saying that. As I said, this is probably the most important slide, so let's stay here as long as necessary.
So first of all, can you write down again, remind me the definition of this joint likelihood ratio? Because that's sort of a weird, unintuitive object, because it depends
Okay, so
somehow
this is,
both
let's
on-
just go a couple slides
depends
back.
both on observables.
Actually,
and on,
it only really depends on the pattern level momenta that were generated on the way. It doesn't really depend on the observables. I just wrote it here because, well, for one kind of
okay, so it's
consistent notation.
so that I can think of that as just the likelihood ratio at parton level.
Exactly. So
Right.
this is your matrix element ratio.
Right.
And then, yeah. So this I plot here. And it turns out that the likelihood function, the true one, would be the same as the best fit through those points here. This is why they are, in this sense, useful, because we can reduce the problem of finding the likelihood function with fitting a line through these points here.
So I don't understand what you're fitting, but even before that,
Okay.
what's weird to me is that from the point of view of statistics, this parton level thing means nothing. In other words, you're not using any information that we know that in physics there's a relationship between the parton level thing and the real thing,
Okay.
and that's important
So
to us as physicists, but statistics knows nothing about that. This is just some random
Okay,
function.
no. Okay, I put
You see
in
my
some.
question?
Yeah, I put in some physics, particle physics properties in here. So if you think about, or what do I want to measure here? I want to measure some weak scale new physics, right? So the weak scale new physics only comes in at one place, and that's a hard matrix element. These Wilson coefficients don't play a role for detector
I see.
response,
The
or
thetas,
shower,
the
or
rest of it
anything.
doesn't depend on the thetas. That's the point.
And this is what's special in particle physics. That might not be the case for most problems in other fields of science. Or if my parameter of interest would be something that could also affect the shower, like alpha strop or something like this, then this wouldn't really work anymore.
I mean, on the other, I know that I think in some, pardon me for this, Eric, but I think in real analyses you frequently do break that wall, though, in the sense that you fit for things like your jet resolution and experimental parameters like that are fit for at the same time that you're fitting for the theory parameters. So you were saying that this method would not work if you did that. You would have to have some measurement of those parameters ahead of time, and you're not allowing those to float in this analysis. Is that right?
Let's see.
I mean, I know that in practice that's what is done in a lot of experimental analyses.
In some sense, yes. So if this factor, well, if the additional parameters that you have in mind would start to affect something like the detector response or the showers, then you run into problems.
Well, it's not. I don't think that it affects it. It's just that. I don't know. You'd have to.
Well, if
they'd
it's,
have to tell you why
well,
they do this. I think it's somehow it's meant to be more robust because you're
Well,
determining the parameters
well, in
exactly
some
for the
sense,
data set that you're using.
I use a
something like that.
factorization here. So if I look at my likelihood ratio, P of x, c, and theta, or P of x, c, and let's say for the theta prime, then all this is something like the likelihood of x and z
Yeah, I think I can give you an
times
example.
P of z and theta over P of z and theta prime. So as long as you can write it in a way that there is no additional parameter that affects how my pattern level momenta are reconstructed into observables, then you're fine. Once you have a parameter that would change that, so that you can't
So
write it
I
like
think I
this
can give you an
anymore.
example, because it sounds
Yeah,
crazy,
totally.
right? Why should you, how can these depend on, yeah, but I think it's more that it's a dependence on the data set. So for example, if you're worried about some jet faking a lepton,
Yeah.
okay, you might be, that probability may be bigger if you're in a data sample that has more jets. Or, you see what I mean? Because,
No, but for a single jet, it
Maybe-
shouldn't matter. Like the fake rate of jet to lepton should be the same, independent of what your Wilson coefficient is, right?
theoretically, but it's actually not. If you have a lot of jets, right, then you have overlapping effects. Maybe this is not the best example, but I think that a lot of analyses contain these kinds of probabilities, but they actually fit for them as nuisance parameters in that within
Well,
that analysis.
We will do that later too,
Okay.
but kind of assuming that it still factorizes in the way that the let's say the jet fake rate or lepton fake rate should not depend on what the actual underlying theory parameter is, which
Yeah. Okay.
is not the worst assumption to do, right?
But so then I can ask okay, I understand. So then I can ask my other. So what are you fitting?
Okay, so these points here tell me that for a given event at pattern level, how much more likely is the orange theory versus the red one? And well, if I run it through the detector simulation and all the other stuff, typically things don't change so much. So you would expect that, well, it should roughly follow the same shape, right? Just to get some intuition. Like the fact that high PT events are more likely to be the orange versus the blue theory won't depend on any physics effect or any detector effects, right? Just intuition-wise.
You say if you fit blue point only and or only fit the orange point only, you should get the same curve.
Oh yeah, I'm saying that.
But
Then you, in principle, you don't need to do the origin curve.
No, I don't need to. I just did that for, well, pedagogical purposes of seeing those both sets and how different they look.
You're also assuming that this is in some sense a monotonic function, an invertible function, because
It doesn't have to be a monotonic function, right?
no, but invertible. I mean, in the sense that
What do you mean with invertible?
In this function here, the different log likelihood ratios give you different values for the observables, right? But that may not be true in general, right?
It's a different log likelihood.
This one is monotonic. You're saying it doesn't have to be monotonic.
No. I don't think it has to be invertible. Like, do we ever want to invert it? We just want to evaluate it,
Yeah.
right? And keep in mind, I haven't actually shown you the proof that this is really true. Like that this is that this best fit is really the likelihood ratio.
So what do you, so say again, show again, what do you minimize to find that?
Okay. So at the end, so I said that if you can show that if you construct like this loss function here, this is a simple one, and try to find this R of x that minimizes this loss function here. You see there is a term here which is our joint likelihood ratio, and there's some function here that has the same form as our likelihood ratio. So this depends on z, this one does not. And if we try to find a function R of x and theta that minimizes this loss function here, I claim that this function here is the actual likelihood.
So the sum is sum over all possible z?
Over all events. Well, it should be like an integral over events or sum over events. So in this case, it's a set of unweighted events, so it's just a sum over events.
And that follows for any, this is, as a mathematical theorem, this is for any function. So this, what you're inputting is the true R of x and theta is some sort of a convolution of the R of x and theta with some parameter, with some other, but in a way.
So your curve is the
convolution that
final.
doesn't depend on
Okay,
theta.
so this one here is my black curve, and
Yeah.
those one here are my colorful points.
Yeah.
And I try to find the function here.
The
a
crucial,
black
the
curve.
crucial thing is that thing is a convolution of the
Yeah.
original thing, and that convolution has no dependence on theta. That's the crucial assumption here that makes this mathematical theorem true, right?
Wait,
R of x and theta is the true thing that we're looking for, right?
yeah, so this R, yeah, this is a true thing.
Yeah.
This is R of x, z, and theta, so which is actually just R of
Yeah.
z and theta, but well, sampled for the same point at z.
I think I
Yeah.
understand.
So there's actually no x dependence here.
Okay.
Okay. Maybe I should have started the other way around, explaining this and then say that at the end this is nothing else than fitting the line. Like if you try to find it or want to interpret it in a simple way in this 1D example. Okay. So my claim is that if you have a parameterization of a network that would parameterize this function here that is sufficiently expressive, and you do this minimization here, so you efficiently train your network with enough data, then it will learn this likelihood function. Okay. So there.
So can I just ask, so
Yeah.
you've shown an example where this is a one-dimensional
Yeah.
distribution, so you can do it in a
Yeah.
block. But okay, but when you now you want to, of course, you want to try to go to higher dimensions. But why is going to higher dimensions with this any better than going to higher dimensional distributions? I mean,
We
it
say-
seems like you have to, in both cases, you have to just simulate enough data that you can, and then you have to do some machine learning fit.
I see.
What is the difference? Why is this better
compared
than-
to like the usual machine
Yeah,
learning
the sort of,
things?
when you have a bunch of higher dimensional distributions.
Well, one thing is that if you think about, let's say you have two theories that are more similar, so where this is all like order 1. Okay, so if you just do a classifier that does not know about the truth level or like the pattern level likelihoods as input, it will have a very hard time to distinguish the two distributions. So you need to really put in a lot of data until, well, at least until your statistical fluctuations in the data samples are smaller than the differences of the two distributions, and wait a long time until your neural network has actually figured it out. Here we give it some additional information. We already, for each point, also give it what is at pattern level the likelihood ratio. So it will be much easier for the network to learn those things because we already provide it in the as input.
Well, I think where I see it, maybe, I think what I'm seeing is that what you're doing here is you're computing a function where there is a lot of correlation between the parton level and the thing. So it's an easy, whereas the other thing, you're directly trying to find a subtle difference between two very similar data sets. So you're putting you're putting all this all your computing power is going into computing a function that is a simple function. It's not a somehow.
I provide something that has strong correlations with what I actually want to get at the end.
Right. And you just need to get that
Yeah.
accurately.
Yeah. So it will be, well, for the normal neural network approach, the same statement is true, except that for this one, in many cases, you would expect that enough data means less data than for the normal neural network approach, and sufficiently and efficiently means, well, less big network with less training time. So it's a more practical approach, especially for the case that we care about. Okay, let me just show you the comparison to what I showed you earlier. It's actually the same example I showed earlier with the histograms. So let's compare it to histogram. You will see it takes those events and fills them into histograms and gets a likelihood ratio. You see it's the same result. So here it's with 5 pins, and the green one is with 100 pins, I think. So it agrees well, so that's good. So I hope that gives you some confidence that what I'm doing here isn't complete nonsense. And you can kind of see that as like a continuum limit of histograms with large number of bits. Like, well, essentially that's what fitting is, right? It's going in the continuum limit. And unlike histograms, this more easily translates to well, higher dimensional spaces. So fitting still works if you have like 10 input dimensions, so 10 observables.
It's
Like
smooth just because you chose some
Yeah.
smooth basis of functions,
Exactly.
right?
So you really want to use it for your advantage if you have a high number of observables, and that's the time we live in. We want to do a multivariate analysis. Okay, there's one other cool thing that I have shown in the previous slides, a log likelihood ratio as a function of observable, but it's also a function of the theory parameter. And something that will turn out to be useful here is what's in statistics called the score. So it's defined as a derivative of the logarithm of the likelihood function or likelihood ratio function, doesn't really matter, with respect to the theory parameter. So it says something like, how does my data change when I change my theory parameter? So here I show for the same example that I had on the last slide. So event sampled according to my standard model hypothesis. And the position again shows what's the likelihood ratio, or the joint log likelihood ratio at the point. And those little arrows, the slope shows what is the derivative. And if you would have to fit the function through it, you would see that those arrows really help you like guiding it. You know, it should be something like this. So let's do the fit. And indeed, it's exactly what you would expect. And it's, well, as with all fits, fits work better if you also provide the first derivative and not only the value of the function. That's really the entire statement behind it.
Sorry,
Yeah.
I understand this. What do you plot on this?
So here I show again the arrows show the joint log likelihood ratio. So the same thing I had on the previous slide, but now as a function of my theory parameter.
This is for every data point or for
So I just sampled a bunch of points according to the standard model, and then shows like, well, for each point I randomly chose like calculates the log likelihood ratio.
This just shows the standard model theta equal to 0, and then
No, this is here, and then.
then what's
But
what's on the y-axis? What do you?
Okay. So let's say I have my function r, which should depend on x, z, and theta, right? Okay. Told you earlier, this one doesn't really matter, and this one I fixed to be well 300 GeV. And then, okay, I have the function that just left of theta. So I ask how much more likely is, well, an event that I sampled where my PT of the Higgs is 300 GeV in this theory where theta is -1 versus this theory where it's 0.
Okay, then.
And I find it's 3 times more likely, or e2 is 3 times more likely.
Okay, so everything will
Yeah.
go to 0 at the.
Yeah,
at
so
the,
everything by definition should be 0 here.
Okay.
Yeah. It's just expressing the fact that this is a function that both depends on, at the end, x and theta. Okay, so it reflects the fact that we are solving the problem not only for one parameter, but for all of them at once. And that this is, of course, useful because it should be a continuous function also in theta.
So you
So
have to
knowing
do
something-
do some sample to make this stuff.
Yeah, well, it doesn't really matter what you sample it according to, because at the end what you care about are the values on the y-axis. And it doesn't really matter how you distribute the points in this plot.
But I mean, just to say, for every sample you put a point on this
Yeah.
plot, right? So you have to do some samples in order
Yeah.
to feel the
Yeah.
stuff.
But so,
Okay.
I don't know, for example, you can could take the same set of points and then calculate it for this, and for this, and for this value of theta principle, right? Since it's a continuous function, you can then fit the function through it and solve it for all possible thetas at once. So for all possible series.
In a way, kind of, if you really, the way I'm seeing this is that you're trying to leverage the fact that in BSM physics, we in a sense have a simple theory where the parameters, we know the dependence on the theory parameters very well. And we have a relatively simple representation of those, and you're trying to use that
Exactly.
maximally. You're trying to take maximum advantage of that.
Exactly. Like we know it should be a smooth function, and we just try to learn it.
Yeah. I mean, this R of z theta is kind of, that contains the full dependence on theta, and it's something we know very, very well,
Exactly.
right? And then everything else is just a convolution of that function. This is all built on that.
Yeah.
Right.
Okay. Whew. It's great that you asked so many questions. I was hoping that would happen. You want to ask now?
No, I need to leave soon.
Okay.
Now I want to hear.
He's only got through 2 slides. We're not letting him get his time.
No,
Sorry
no,
about
that's
this,
good.
but
Like,
I'm
it
just
doesn't-
really trying to understand.
Like at the end, there are just more examples, but this was the 2 important slides. So, okay. So, essentially, what we did here is take the likelihood ratio points and the slopes as input, and again obtain some sort of best fit and get this function here. And we gave this kind of approach a name, analysis. It's likelihood, inference. Well, I forgot what the rest of the acronym stands for, but essentially it takes it has a neural network where you put in the observables and the theory parameter, and it gives you out what's my estimated likelihood ratio, and it's trained using both the likelihood ratio and its derivatives, so the score. Okay, so let's try to go quickly through this. Why are the scores interesting? Well, they turn out to be something that we already know is useful in optimal observables. So if you, let's say you take your likelihood ratio and expand it around a point like here, okay, you can write it in a linear expansion like here. If you restrict yourself to live in this neighborhood here, the linear expansion will always be an approximation around this reference point. And so if you live close to the reference point, this approximation is sufficient. So this knowing the score here in some sense is as powerful as knowing the full likelihood function. Close enough to this point here. Okay, I'm just explaining you how to linearly expand the function. But then you look at what is this here. So it's something that only depends on observables. So it's a function of observables. And we know a function of observables is itself an observable. Okay. But since this is as powerful as knowing the full likelihood ratio in the neighborhood, it's essentially an optimal observable. So this contains, if you have n theory parameters, this would be a vector containing n components, so you would get and optimal observables, one for each theory parameter. And so we have found a description on how to find optimal observables. Okay, I think that's cool and useful.
What is optimal, what do you mean by optimal? What is optimal about them?
So if you would live here in this neighborhood, then all you really need to know is this line here to do your likelihood ratio tests. So you only need to know what's the value of the score here, and then you are done. So in this sense, well, this is just a name that's given to those observables in the first place.
I would have thought that optimal observables are, what would be optimal at the end of the day is that you get in some sense, the best possible fit of your theory parameters to the data, but this can't be that.
Well, so if you would fill a
And they are
histogram,
optimal to distinguish
Yeah. So if you want to measure,
theta.
yeah, if you want
okay.
to measure a certain theory
I
parameter,
see.
then if you would fill a histogram with these observables here, you would get the best possible result close
For
to the reference
distinguishing
point.
it from the standard model or for doing what?
Well, to distinguish this point here from the reference point. So to distinguish
okay.
the model from the
Distinguish
reference
nearby
point,
values of
yeah.
Okay.
It's of course a local approximation. It will break down naturally down here, but at least locally it works. And this is very useful for, well, if you have a series that you can expand around a special point, like a Higgs effective field series or standard model effective field series that you can expand around the standard model. So then this is very useful because you have a special reference point, the standard model, and you, by construction, set that your expansion parameters are small. So it might suggest that a linear expansion is meaningful and a good ansatz in the first place. And indeed, these optimal observables are the ones that will be sensitive to interference effects. Right? If you're really, really close to the standard model, it's only the interference effects that you would see, not the dimension 6 reference. Okay. So this turns out to be, for many cases, sufficient, and so we gave it so essentially it's we said we developed a new algorithm that says it takes the observables and returns an estimated score at the standard model point or at some reference point. Well, this method is called, let's see, score approximates likelihood locally, so the Sally method. Anyway, this is also useful for something else. If you like, what you really want to calculate at the end is something like the expectation value of the likelihood ratio. Well, standard model value, it should have a minimum. Well, this is minus 2 times, and then it has some shape around, so you can always expand it with a quadratic function around its minimum. And if you calculate this expectation value, well, we'll have some form like this with some quadratic expansion parameter here. And this is called the Fisher information, and it turns out that this Fisher information can be written this way, so some term that's proportional to the rate, and then some term that is essentially just the sum of scores evaluated at different events. And this thing is really cool. So there is another statistical theorem, the Kramer-Rao bound, that says that the covariance matrix. So this is what we want to measure at the end in experiments. Like, what is the covariance matrix between a reference parameter point, like a best fit point for standard model, with some other parameter. And this is bounded by above by the inverse Fisher information. So essentially, the Fisher information characterizes how well can we measure a theory parameter. And what I've just shown you is a way to calculate it analytically. So if you have a model in mind that you want to probe, and you want to know how well can theorists measure it if they try really hard. And the only thing to answer that question, and the whole can experimental measure, but the only thing you need to do to answer that question is calculate this Fisher information here. And I gave you an analytic way to calculate it, and then you're done. So it's something I find rather convenient for estimating limits in an easy way.
Sorry, what is sigma?
Cross section.
So you're assuming that you're measuring, that's your thing that you're, why is cross-section coming into this?
Well,
As
there's
opposed
some,
to something else, I mean.
so there will be it will somehow depend on the overall rate. This is this term.
So
this is at the end what comes from your Poisson term and the likelihood function. And then it will somehow depend on kinematics. And this is what the second term is.
You're saying that this, so just knowing the distribution of the rates as a function of the theory parameters, this thing already tells you no matter how fiendishly clever you're going to be in your statistics, you can never do better than this thing, which is you can compute just knowing the rates as a function of the frequencies of the different events as a function of theory
you get
parameters.
some information. It just tells you get some information from the rate itself, right?
Yeah.
Typically, theory parameter changes the rate,
Yeah.
and if it doesn't, well, then this term here is 0, right? So you get some information from the rate, but you get additional information from distributions.
The rate for what? I mean, this is
For,
there are
like,
many different cross sections I could measure. So
This is the total cross section. The total cross section in your event sum. Like you, well,
So
let's say
that seems really weird to me because I don't understand that because, so for example, I could imagine some theory parameters that don't change the total rates at all,
yeah,
but they change distribution.
yeah. Then you only get information from distributions, but not from measuring the rate, right?
So this is, yeah, so this is the amount of information I could get by measuring sigma. This is telling
Yeah,
you, if I,
but-
okay, so then sigma
but-
is the thing I'm measuring.
Well, one thing you measure is the total cross section, right? So the
Sure.
number of events,
Sure.
right? And this is proportional to the derivative of the cross section with respect to a theory
Yeah, but
parameter.
when you say the covariance matrix, you mean the covariance matrix if only you're measuring is the total cross section?
No, this is a covariance. Okay. Depends on what question you're asking. So I say, this is the best possible, or well, this is the covariance matrix that, let's say, an experimentalist can measure.
By measuring
And-
infinitely many distributions,
Everything.
everything.
And I say it's bounded by the inverse of the Fisher information, which contains information from the rate, and it contains information from distributions.
It's just weird to me that one particular observable, the total cross section, would give you this bound. Right?
It's more than the total cross section. It's the
No, the IJ, oh, there's this, I guess there's the
T's, the
scores.
scores.
Yeah,
Yeah.
He evaluated
Yeah.
on those big two slides,
Yeah.
okay.
involved all the information that he had.
So keep in mind that when I had the likelihood function in the first place, this was an object that's normalized to
Okay, I
1.
got it. Right.
So you have a term that says something like the overall number of events, and
No,
then
I-
has
I-
another
that's
term
right.
that
I
says
got
how
it.
those
Yeah,
events
yeah.
are distributed.
Okay. I
And,
got it. This is just the sort of the rate term. The
Yeah.
Poisson term. Good. Okay, sorry.
It's really just a Poisson term. If you write it out and do a half a page of math, you end up with this.
Okay.
Okay. And yeah. So okay. Why is that cool? Well, okay. So this is a simple object. It's just an n by n matrix. If you would want to calculate it, I'll show you an example on the next slide. It's actually independent of how you parameterize your observables, and it should be, right? It shouldn't matter if you how you what units you give your observables or how you parameterize them, as long as you have them all. It's covariant under reparameterization of your series space. So if you like the one basis and you like the other basis, then you only have to multiply by Jacobians, and then you can compare each other. It's additive between experiments and phase space regions, so that's cool. It's easy to include systematics. I might skip that point in the interest of time. I think I'm only 5 minutes over time. And for those of you who like geometry, this object here has the defining properties of a Riemannian metric. So it defines a Riemannian metric, so you can do geometry with it. And if you look at this is something like a distance here. And if you, well, it's kind of, if you think about the parameter space as a manifold, then what we have done here is essentially put a tangent plane on the manifold and look at our distance there. But you could also imagine to, well, get distances along geodesics to define distances, and therefore these expected likelihood ratios. So there's some interesting connection to geometry that if you're more interested in the work paper a couple of years ago. Okay, so let me try to go very quickly and skip some slides. Okay, let's skip this. We wrote a tool that can do everything I just told you. It has all of what I just said and what I will present in the next slides implemented, and probably the most important thing, it has extensive documentation, it has easy to use tutorials, and if you want to install it, you only have to type in pip install MadMiner. I don't know how much you install codes, but when I was a student had to install them, I always hated it, but this is super easy. Okay, here are some faces on people who developed it and used it. And let me go through one physics example. It's essentially the same I showed before, just that now I have 48 observables, and I have 3 theory parameters, so going to like the real case that we care about, the multivariate case with many parameters. Spend some time expanding the Fisher information, so let me show one to you. So I said I have 3 theory parameters, so my Fisher information should be a 3x3 matrix, and indeed it is. And it describes at the linear level, so if I only care about the kind of linearized likelihood ratio, it describes how sensitive am I to different parameters, including their correlation. So what we can do is we just use the Cramer-Rao bounds that I showed you before to get some exclusion limits. So yeah, essentially plot that and plot your limits, and then you can start to immediately see some interesting physics out of it. For example, we can get the Fisher information just from the rate term. Let's say we only measure the cross-section, and we would get what's those light gray lines here. So if we only have one observables, we can only constrain one combination of parameters. So we get like this band here. Then we can ask, what is if we only look at the distribution term? So let's say we only have normalized distributions, but multidimensional. We get like these dashed lines here, and you can see, that breaks the degeneracy along this blind direction. And it's almost as good as the rate in the rate-sensitive direction, actually. So that's a selling point for looking at distributions. Distributions are really powerful, more powerful than just a simple rate. And we can easily combine them by, well, just adding up 2 Fisher informations. And then we get those limits. Let me skip systematics. If you care about it, ask me afterwards. I'll skip that too. You might ask, how good is that? So the Fisher information and the scores that I showed you earlier, like the optimal observables, they in some sense use that, or they explicitly use that I do an expansion around a single parameter point, in this case a standard model. So if you're far away from the standard model, this of course is expected to break down. In my example here, this is exactly what happens. I show again here my dash curve is the same thing as Fisher information. Then I introduced earlier those optimal observables. So what I can do is take my observables and fill them into histograms. And that should be kind of optimal, ideally. This is what's shown in the blue line here. And you see, oh, that doesn't really agree with our Fisher information. And that's how it is. And then we can also just estimate the full likelihood function, which is the red line here. And it again shows a different result. But at the end, that's not too surprising because in my pedagogical example here, we have very few events in the first place. So we have probed very large Wilson coefficients, and the dimension 6 square terms only contribute between 1 and 10% to the total cross section. So of course we expect them to play an important role, and therefore our local ignoring their approximation wouldn't be so radical in the first place. But yeah, here I show it's kind of the money result plot for my simple example process. So here are for 2 parameter planes, we show the results for if you only look at the rate. So again, you have to generally see this in one direction. You only look at a 1D histogram, that's in green. You only look at the optimal observable in blue, and you look at like the full likelihood function in red. And you can see that using these multivariate methods here, you can go significantly beyond a simple, let's say, 1D histogram. If you think about how much more luminosity would you need with a simple 1D analysis or histogram analysis to achieve the same limits, that would probably mean to run the LHC another 20 years longer, but using sophisticated but still efficient multivariate methods like the approach that I presented here can do the same thing. So I think in the era of data that we start to live in, this is something that we should consider doing. For theorists, like I guess most of us are, I think this approach is very useful since we can get things like optimal limits kind of automatically without thinking too much about it. Like you get your final result as kind of first step of the analysis, and then you can start to ask interesting questions like where in phase space is my information? So what I show here is on one hand the cross section as a function of an observable, in this case again the PT of the Higgs, but so this is the gray histograms, but also the Fisher information as a function of this observable. So you can look where is my information. So which is the region in phase space where I get most information from, so that's most sensitive to those physics parameters. And this is kind of the question that you would like to know the answer to, but typically you do a lot of try and error to find it out, but here you get it out for free in the first step of the analysis. So it really gives us the physics intuitions that we would like to have at the detector level, in an efficient way, utilizing the power of machine learning. Okay, that's essentially it. So thank you for listening. And sorry for being over time, but I think we had
overtime. I have to apologize. So
I think we had a nice discussion in the middle, and if you understood
no, it was really totally my fault.
Yeah, if you understood how the method works, then I'm totally happy and I have achieved my goal. Maybe you find a way how to apply it in whatever problems you are working at. So my colleagues have also applied it to looking at strong gravitational lensing, which has nothing to do with LHC physics, but the methodology still applies. So maybe you can find a be useful too.
Why they call it MadMiner?
Well, it's an add-on to MadGraph, right?
Sure.
So Mad and then, well,
Manner.
Mad is for Madison, not
Yeah.
for crazy.
Okay.
Yeah. And miner because the previous paper we had was called mining gold from simulators. That's what
Data.
MadMiner.
Data.
Yeah, data mining.
Okay, so let's thank the speaker again.
So I have to go home because I have to get my dog home. So can you just let are you up for dinner?
Yes.
Just text me, tell me whether you
We're going to
decide.
be here at 6, so we'll get
Yeah.
there. I mean, he's not even ready.
Yeah, so that I have to leave now, so I'll leave my house at 6 and I'll meet you wherever.
6:15.
Yeah, I can be
It's only
anywhere.
like
Yes.